Okay, here you go.
EE World, I'm Martin Rowe. We are at Apec 2024 in Long Beach, California. I'm here with Mike Schnecker of Rohde & Schwarz, and Mike's got a setup here using the Rohde & Schwarz MX-05 oscilloscope, and he's got about 10 buck converters going on here, and we're going to be looking at some load step response testing. So Mike, why don't you tell us about your test setup?
Okay, so basically, Martin, we've got our new MX-058 oscilloscope. This is the world's first 8-channel oscilloscope that will capture up to 90% of real time. So really fast processing. And what I'm trying to show here is what you can do with 8 channels. What kind of measurements can you make? So I've chosen a multi-phase buck converter here. This is a 10-phase design. As you mentioned, there are 10 individual buck converters, all driving the same load in parallel. And one of the things about these kind of buck converters is a lot of signals to measure, right? So traditionally, what you care about is the flatness of the voltage delivered when a load step happens. And so we've got a load step here. This is just a resistor that switches in with a pair of transistors that are driven by our pulse generator. This is connected to the internal pulse generator on the scope. It's a 2-channel 100 megahertz ARB, so we can generate a pulse with that. And the pulse is driving the load, and you can see here, and actually I'll select the right waveform. This is the current step, the blue waveform, and you can see it goes up to about 140 amps from 0. And the voltage trace is below that, and that shows how the voltage rail changes a little bit. That's about a 20 millivolt dip in voltage, and then the signal recovers, and you got a little bit of an overshoot after the load is removed rather abruptly. So that's kind of the basic in out stuff, but when you're building a system with this many nodes to it, you might want to look at, for example, what the switching nodes are doing. So what I've done is I've taken 16 logic channels, I'm sorry, 10 logic channels, and connected them to the 10 switch nodes of each one of the buck converters. And I've got a logic trace that shows all of them. So this is all of those switch nodes operating at the same time, all 10 phases. And you can see that sort of the pulse widens out here and it goes away here. Well, that corresponds to the load step. When the load step happens, all of the phases widen their pulse, and you can see that in this purple track, which is the track of the pulse width versus time for all 10 phases. So we're seeing how they get wider, and then once they recover the current, they go back to its equilibrium. There's a little bit of overshoot there. And then when you get to the end, you see they all stop for a moment to allow the inductors to drain the current off, and then you start your regulation again. So the nice thing about having all these channels, I can now diagnose the operation of the feedback control, which is pretty complex in these setups.
Yes. Okay. So what is this on the scope here? It looks like a white trace. Looks like it's coming over here, and it goes up, comes back down, maybe a little
overshoot.
Overshoot, and then levels off. So what is that white trace?
That is the current being delivered to the load as a function of time. So when the load step happens, it goes, you can see it starts at 0, and it's up to 140 amps, and then right down a little bit of a reverse current when it shuts off because there's no load, and so it's drawing current back in to the inductors. But you see that when that happens with a load step.
Okay. All right. Thank you, Mike.
Cool, man. Thanks a lot.
All right.
Martin.
Thank you.